Sound is propagated by longitudinal waves. As a sound wave passes, the medium undergoes compressions and rarefactions. Sound propagation depends upon the density and compressibility of the media. A small region of width delta x contracts and expands as the wave train passes. In such a small region, the density of the medium changes as the wave pressure increases and compresses the gas or the liquid. Pressure fluctuations depend upon the density and the compressibility of the medium. The Doppler effect is the change in frequency when the observer moves, the source moves, or both the observer and the source move. We treat here only mechanical waves, and the treatment does not apply to light, which also displays the Doppler effect. However, light propagates at constant velocity, independent of the speed of the source. Simply stated, frequency is the velocity of sound divided by the wavelength. Assume the source moves, the wavelength is modified. As the observer moves, the relative sound velocity changes. As the observer moves towards the source, the observer encounters, per unit time, more waves than if not moving. Moving away, the observer encounters fewer waves in the same time period. As the source moves, at each position, when the wave is emitted, the wave moves out in a circle or sphere from that point. Once the wave has left the source, it forgets about where the source is and just keeps on propagating out. Hence, the wavelength is shorter in front and longer behind the source. This treatment considers the source is moving towards the observer in a straight line. To treat the Doppler effect, first write down that the frequency is the velocity of the wave divided by the wavelength. If the observer moves, then the velocity changes, and if the source moves, then the wavelength is modified. Choose the signs based upon your physical intuition of what is happening. Do not try to memorize the signs of these 4 different cases.